So let's go through one example of using activity coefficients just to show like how this would affect a calculation involving equilibrium. So our example is we're going to look for what's the concentration of calcium ions in equilibrium where we have a few different things present. So we have a calcium fluoride solid, and it's a saturated solution, so we have calcium fluoride solid present as a solid, and then with 0.050 molar sodium fluoride present as well. Okay, so we can assume there's going to be very low concentration of calcium. Calcium fluoride is an insoluble salt, and that's borne out by the KSP value. KSP is 3.2 times 10 to the minus 11. So this is a very small equilibrium constant. We expect mostly this is going to stay in the solid form. But to find this in terms of activity coefficients, we need to use activities instead of concentrations for our KSP. So everywhere we would normally put a concentration, we put an activity. So our equilibrium coefficient is equilibrium constant is equal to the activity of calcium times the activity of fluoride squared. Or we can rewrite this in terms of concentrations. Concentration of calcium times the activity coefficient for calcium times the concentration of fluoride squared times the activity coefficient for fluoride squared. Okay, so the first thing we need to know is what is mu? What is the ionic strength? All right, because we do have the sodium fluoride that's already present. So that's going to be equal to 1/2 times the concentration of sodium, which is 0.050 molar, times positive 1 squared plus 0.050 molar times negative 1 squared for fluoride, which gives us 0.050 molar. So our ionic strength is equal to the concentration here, and this is true for any 1-to-1 salt. Once we have 2-to-1 and different charge states present, that's not going to be true anymore. Okay, and so what we need to know then is what's gamma for calcium and what's gamma for fluoride. We can look this up, table 8-1, the one that I showed in the previous video. We can look up the values of activity coefficients. So gamma for calcium is 0.485. Gamma for fluoride is 0.81, and these come from the Debye-Huckel equation, but we can just look up the values because we need to know the ionic radius anyway, and that's in that table. So what we want to do is then take our equation up here that I've hidden behind my face and rearrange it for calcium, right? That's what we're trying to solve for, is what's the concentration of calcium. So the concentration of calcium is going to be equal to KSP divided by all this stuff here. Again, it's hidden behind my video here. But so we'll have gamma for calcium 2 plus. We'll have the concentration of fluoride squared and gamma for fluoride squared. Okay, and then we can just plug in all of our values. So we'll have 3.2 times 10 to the minus 11 divided by 0.485. Concentration of fluoride is 0.05 molar. There'll be a negligible contribution from the calcium fluoride. We can ignore that. Our concentration is going to essentially just be due to the sodium fluoride, and that needs to be squared. And then we have our 0.81 squared for our fluoride. Okay, and then we can plug this in and calculate a number. Let me give myself a little bit more space here. So that is equal to, I've already done this calculation in advance, 4.0 times 10 to the minus 8 molar. Okay, so what if we did this instead without activities? How much of a difference does this make? And essentially the one thing that changes in this calculation is that we would, right, so if no activities, no activity coefficients, we would just eliminate these. Everything else about the calculation would be the same. This one I haven't calculated in advance, so let me pull up my calculator and we can see how much of a difference this makes. All right, so my calculator over here where you can see it. So 3.2 times 10 to the minus 11 divided by 0.05 squared. And we get 1.3 times 10 to the minus 8. So, it's still the same order of magnitude, but, the solubility increased by almost a factor of 4, which is a pretty significant difference. So, not taking activity coefficients into account would give us a pretty large percentage error in terms of our expected concentration of calcium. So this is an example of a case where it really matters, where it is important to include that activity coefficient. It gives us a fairly different answer than we'd expect. One final note about activities in this last video is, some things that we have defined previously in terms of concentrations are actually defined in terms of activities. The main one being pH. So pH is actually defined as the negative log base 10 of the activity of the hydrogen ion, not the concentration of the hydrogen ion. And so this actually has this extra term of the activity coefficient that's present. So a pH meter will measure activities. And that's actually true for our other electrochemistry type sort of experiments. Because they're measuring equilibria, and the equilibria involve activity coefficients, we actually measure activities. So if we want actual concentrations, we have to take the activity coefficient into account. So ionic strength affects pH. That's something that's important to know. So anyway, that's just an aside. And this will show up in some of our future classes. For the most part, we aren't going to use activity coefficients extensively, but they do show up occasionally, and it is something that is important to be aware of.